This fourth trailer video development board is an overview of the PIC Micro-X development board series and is followed by 5 sets of PIC device tutorials, each with an episode series number. Starting with the 8-pin PIC12 F1572 episode 10 series and ending with the 40-pin PIC16 F1789 episode 14 series device tutorials. These PIC devices are the same as used for the breadboard series tutorials, but the complexity of the development board episodes increases, taking advantage of the added features and compact design of this development board. The PIC Micro-X development kit is comprised of 2 boards, the main board below and the trainer board mounted above. Here the PICKit4 is connected to the PIC Micro-X kit, and here the Snap programmer connected. Here is an example of jumper wires used to connect the main board and trainer board headers, which I'll explain shortly. I'll also explain how to use a ribbon cable to connect main and trainer board headers. Now with the main and trainer boards side by side, the jumper wire example used the main board header labeled RA20 and had been connected to the trainer board's switches header. Let's take a closer look at the main board header RA20. The graphic on the right with the pins of RA20. Note the orientation of this graphic matches the actual RA20 header. A keyway below, as seen on the printed circuit board, assists with the correct alignment of the ribbon cable's connector. With pin 1, or the ground positioned here, we'll use black jumper wires for ground in tutorials. Pin 2, or the supply VCC positioned here, we'll use red jumper wires for VCC supply in tutorials. Pin 3, or bit 0 positioned here, we'll also use black jumper wires for bit 0s in tutorials, following the resistor color code value. Pin 4, or bit 1 positioned here, we will use brown jumper wires for bit 1 in tutorials. Pin 5, or bit 2 positioned here, we will also use red jumper wires for bit 2 in tutorials. Pin 6, or bit 3 positioned here, we will use orange jumper wires for bit 3 in tutorials. Pin 7, or bit 4 positioned here, we'll use yellow jumper wires for bit 4 in tutorials. Pin 8, or bit 5 positioned here, we'll use green jumper wires for bit 5 in tutorials. Pin 9, or bit 6 positioned here, we'll use blue jumper wires for bit 6 in tutorials. Pin 10, or bit 7 positioned here, we'll use violet jumper wires for bit 7 in tutorials. Note pins 9 and 10 of RA20 are not actually connected to the 20-pin socket due to 8, 14 and 20-pin devices not having pins RA6 and RA7. The 10-way header configuration applies to devices with a full port, that is to say, a device with port bits from 0 to 7. This will become clearer once each device's available port pins are presented. Below is a 10-way ribbon cable. Always align the ribbon cable's keyway to the orientation marking on both boards. Normally header pins would have a surrounding casing, with the keyway preventing the ribbon cable connector being connected incorrectly. Therefore pay attention to align these keyways to prevent potential board and PIC device damage. The main board header, RE, is a 6-way header, using the same pin configuration as the 10-way up to the 6th pin. The 6th pin of header RE is connected to pin 1 of 40 and 28-pin sockets, as well as the 6th pin of header RA20 for the 20-pin socket on pin 4 and pin 1 of the programming and debugging connector. All these interconnected pins allow the MCLR function to access any of these 3 sockets for an installed device during programming and debugging. For those who missed the first trailer video, the main board has 3 sockets for installing PIC devices: the 40-pin, the 28-pin, and the 20-pin, used with 8, 14, and 20-pin PIC devices. The trainer board has 8 switches, 8 LEDs, a buzzer, potentiometer, EEPROM socket with 2 I2C headers. The 40-pin socket will be used for the PIC16 F1789 device. Note the socket's notch on the right and on PIC device, as indicated by the half circle on the diagram on the right. These must be aligned on top of one another for correct installation. Device pins RA0 through RA7 highlighted are used with the main board header pins labeled RA. Device pins RB0 through RB7 highlighted are used with the main board header labeled RB. Device pins RC0 through RC7 highlighted are used with the main board header labeled RC. Device pins RD0 through RD7 highlighted are used with the main board header labeled RD. Device pins RE0 through RE3 highlighted are used with the main board header labeled RE. Note, as previously mentioned, MCLR is connected from programmer port pin 1 to RE header pin 6 and pin 1 of the 40-pin socket, as well as the other 2 sockets' MCLR pins. Therefore, only one PIC device can be installed in any of the 3 available sockets at one time for programming and debugging. The 28-pin socket used with the PIC16 F1718 device. Here, the socket notch is found at the bottom, so the PIC device is installed with its notch also positioned to the bottom for correct installation. Device pins RA0 through RA7 highlighted are used with the main board header labeled RA. Device pins RB0 through RB7 highlighted are used with the main board header labeled RB. Device pins RC0 through RC7 highlighted are used with the main board header labeled RC. Device pin RE3 highlighted is used with the main board header labeled RE. Note, MCLR is connected from programmer port pin 1 to RE3 on header pin 6 and pin 1 of 28-pin socket. Then the 20-pin socket with the PIC16 F15345 device, the notch positioned on top here. Device pins RA0 through RA5 only, highlighted, are used with the main board header labeled RA20. For PIC devices installed in the 20-pin socket, MCLR is connected from programmer port pin 1 to the 20-pin socket pin 4 and uses the main board header RA20 pin 6. Device pins RB4 through RB7 highlighted are used with the main board header labeled RB20. Device pins RC0 through RC7 highlighted are used with the main board header labeled RC. Next, the 14-pin PIC16 F1705 mounted in the 20-pin socket, with the notches positioned above each other, assisting with the correct location in the 20-pin socket. Device pins RA0 through RA5 highlighted are used with the mainboard header labeled RA20. Device pins RC0 through RC5, highlighted, are used with the mainboard header labeled RC. The 8-pin PIC12 F1572 is also installed in the 20-pin socket, as highlighted. Here, the actual device is installed to confirm both socket notch and device's notch are positioned above each other, ensuring the 8-pin device is correctly installed in the 20-pin socket. The PIC12 F1572 8-pin device only has port A, pins RA0 to RA5, and port header pins RA20 are used. Now that the sockets and main board header pins have been covered, let us look at some of the other features of this board. Here, the mini USB socket can be used to power the board from a computer USB port or external USB power supply unit. If a programmer, such as the PICKit3 or PICKit4, is set up to supply power, then this mini USB port is not used. There is a voltage regulator for 3.3 volt supply if required, and there is a VCC selector that can then be set for either 5 volt or 3.3 volt. There is also a header for 5 volt or 3.3 volt. If PICKit3 or 4 is powering the board, then this header for 5 or 3.3 volts, as well as the voltage regulator, are not used. Here is one of two I2C 6-pin headers available on the main board. There is an onboard 8 MHz oscillator available for use if required. The selector CLK RA7 is used to select either CLK for using the onboard 8 MHz oscillator or RA7 pin. If RA7 is selected, the device's internal oscillator needs to be set up. This selector is used for 40 or 28-pin devices only. There is U2, a quadruple 2-input NAND gate, used for the clock generation and programming circuits. There is U1, a USB to serial UART interface, used with the UART dual jumper selector for either 28 and 40-pin devices or for 20-pin device UART selection. The 6-pin UART double jumper selector. The left jumper is used to select TX or transmit for either 28 and 40-pin sockets, or for TX of the 20-pin socket, and the second jumper is used to select RX or receive for either the 28 and 40-pin sockets or for the RX of the 20-pin socket. Here, TX and RX jumpers selected for 28 and 40-pin sockets. The jumpers are connecting the center pins to the top pins for the 28 or 40-pin sockets. Here, TX and RX jumpers selected for the 20-pin socket. The jumpers are connecting the center pins to the lower pins for the 20-pin socket. There is also a selector CLK RA5, which is used to select either CLK for using the onboard 8 MHz oscillator or RA5 pin. If RA5 is selected, the device's internal oscillator needs to be set up. This selector is used for 8, 14 or 20-pin devices only. There is a header for ground and VCC if required. There is a 6-pin programmer debugger header connection. Here is the second of the two I2C 6-pin headers available for I2C communication applications from the main board. There is also a manual reset button if required. The trainer board has a 10-pin header for switches, a 10-pin header for LEDs, a 10-pin potentiometer header, a 6-pin sounder header for the buzzer. Here are two resistor network components, RN1 and RN2, used with the switch and LED circuits. RN2 is used with the LED header. The number 102 for surface mount components has the first two digits value of 10, and the 2 is for the 2 extra zeros added, so 10 plus 2 zeros has a total resistor value of 1000 ohms. Here, the resistor network pin numbers are associated with resistor color codes for easier diagram reading. This resistor network has two commons on pins 5 and 10, and from 1 to 4 and 6 to 9 there are 1000 ohm resistors between the commons. Let's look at the LED 0 circuit connected to LED header pin 3 on the trainer board. Supply VCC on pins 5 and 10 passes through RN2's resistor R1 and then LED 0 and on to the LED header pin 3, which is then pulled to a high state due to being connected to VCC. Now let us look at a simplified circuit of what we have just spoken about for clarity. VCC supply is connected to the commons of RN2, pins 5 and 10, and passes through the 1K resistor R1 and to RN2 pin 1. So the anode or positive connection of LED 0 is connected to VCC, which has the current limiting resistor R1 preventing excess current flow through LED 0. The cathode or negative connection of LED 0 is connected to LED header pin 3, which is said to be pulled high. If connected to ground, the LED circuit will be completed and turn on. This is the basic circuit of LED 0 on the trainer board. Now we will look at connecting to a main board PIC device header pin. PIC devices may have multiple header connections available, such as with the 40-pin PIC device header RD. Now we can use a jumper wire to connect the trainer board LED header pin 3 to the main board 40-pin PIC device header RD. Here also pin 3 or PIC device port D bit 0. The connections can be made to any available pin on the header RD, say pin 5 as seen here, for bit 2 of port D for the 40-pin PIC device. Using jumper wires allow easy flexibility using the PIC Micro-X development kit. A 10-way ribbon cable connects the trainer board LED header to the main board RD header, and all 8 bits of a port are connected as well as the required VCC and ground pins. This quickly allows 8 LEDs to be controlled from any PIC device's available header, although it requires all pins to be available. When writing code, always remember an LED is turned on, active, if that port bit is set low or 0. This is referred to as syncing and is the preferred method rather than sourcing circuits, which will be covered in the breadboard device tutorials. RN1 is used with the switch's header. The number 103 for surface mount components has a value of 10, and the 3 is for 3 extra zeros added. So 10 plus 3 zeros has a total resistor value of 10,000 ohms or 10K. The RN1 resistor network is in the same configuration as the RN2 1000 ohm network with two commons on pins 5 and 10, and from 1 to 4 and 6 to 9 there are 10,000 ohm resistors between the commons. Let's look at the switch 0 circuit connected to switch header pin 3 on the trainer board. Supply VCC on pins 5 and 10 passes through RN1's current limiting resistor R1, and this time connected directly to switch header pin 3, pulling the pin to a high state. The switch 0 is also connected to pin 3, with a normally open contact. The other contact of the switch is connected to ground. When switch 0 is pressed, the whole circuit is taken to ground or sunk. The switch circuit is said to be active low. When pressed, the pin goes low, else it is pulled high. The potentiometer uses the pot header pins. The schematic shows pot header pin 1 connected to ground and leg B of potentiometer. Pin 2 is for AVCC or analog VCC and leg A of potentiometer. This analog VCC can be connected to a specific voltage level, such as 3.3 volt header pin or the board's default 5 volts VCC. This AVC pin is not connected to the rest of the trainer board's VCC pins, so allowing a specific voltage to be used for the pot supply. This will be covered in detail in later tutorials. The pot wiper is connected to pot header pin 3, and the rest of the pot header pins are not connected. The buzzer is connected to the 6-pin sounder header pins. Pins 1 and 2 are again for ground and VCC, and pin 3 is connected to the piezoelectric sounder. The rest of the 6-pin header pins are not connected. The circuit for the EEPROM socket with a notch for locating pin 1 and the 2 I2C 6-pin headers. The 2 I2C header pins are connected in parallel but marked in and out, and to the socket. More details on this will be covered in tutorials later. Thanks for watching. The next featured video is Curiosity Nano for more details of the series using the Nano adapter and evaluation boards. The breadboard series tutorials will become available first after the 5 trailer videos introducing PIC Micro Tutorials. The development board series will then be released and the Curiosity Nano series tutorials will follow. Please leave a comment or suggestions to help improve the content. Like, subscribe, and hit the notification bell to receive updates on videos as they become available.